Welcome. So today we are going to dive deep into the world of C programming. Now, don't worry, the goal here isn't to turn you into a coder by the end of this. Not at all. It's about understanding the basic logic, how we actually talk to computers. It's the blueprint that so much of our modern world is built on. So yeah, let's get started.
So here's the big problem, right? Computers are incredibly powerful, but at their very core, they're kind of simple. They only get two things, on or off, a 1 or a 0. That's it. This binary language is called machine code. So the real question is, how in the world do we bridge the massive gap between our complex human thoughts and this, super simple two-word vocabulary? And that's where the programming language comes in. It is such a brilliant solution. Think of them as these incredibly sophisticated translators. They take our instructions, written in a way that we can actually understand, and they convert them into the raw ones and zeros that the computer can finally execute. They're the bridge between what we want and what the machine can do. And honestly, the story of how we built that bridge, that's pretty much the story of modern technology.
And yeah, this bridge, it definitely wasn't built in a day. The history of programming is really a story of evolution. It's been this constant journey to make these languages more powerful, more efficient, and most importantly, way more intuitive for people like us to actually use. This timeline really shows you the whole journey, and it's pretty incredible. We started at the first generation, 1GL, where you were literally programming in ones and zeros. I mean, can you imagine? Then 2GL was a huge leap. We got symbolic instructions. But the real revolution was the third generation, 3GL, with languages like C that let us write complex logic. And from there, languages just got more and more abstract, letting us focus on the problem we're trying to solve, not all the tiny steps the machine needs to take.
And this gets to the heart of the trade-off, The low-level machine language is blazingly fast. I mean, it's the computer's native tongue, but it is a total nightmare for humans to write and debug. So high-level languages flip that whole equation around. They prioritize being easy for humans to read and write. And that shift, that was the key that unlocked programming for millions of people and made the software world we have today possible.
So how does that translation from human language to machine language actually happen? Well, there are two main ways: compilers and interpreters. Think of it this way. A compiler is like translating an entire book into another language before you even read the first page. It's a lot of work up front, but once it's done, reading it is super fast. An interpreter, on the other hand, is like having a live translator with you, translating sentence by sentence as you go. It's slower overall, but if you make a mistake, you find it immediately. C uses a compiler, which is a big reason it's so fast.
So let's zoom in on that third generation of compiled languages, because one language in particular just found the perfect sweet spot. That language was C. It struck this incredible balance between raw machine power and human-friendly logic.
And this, right here, is the secret sauce. C is called a middle-level language because it combines the raw power and direct hardware control of a low-level language with the readability and structured thinking of a high-level language. This gave programmers an amazing toolkit. It was literally the best of both worlds.
And that's why C just exploded onto the scene. Your code was portable, so you could run it almost anywhere. It was incredibly fast and efficient, but it still let you think about problems in an organized, structured way. And that flexibility meant you could use it for pretty much anything, from building an entire operating system to the apps that run on top of it.
So what are the actual building blocks of a C program? What's in the toolbox? Let's take a quick look at the essential stuff every developer uses.
Okay, so first things first. Everything, and I mean everything, starts with the algorithm. Before you write a single line of code, you need a plan. It's like a recipe. It's the pure logic for how you're going to solve your problem.
So let's take a super simple example. To add two numbers, the logic, the algorithm, is dead simple. You start, you get two numbers, you add them together, you show the results, and then you stop. That is the blueprint.
Okay, so you've got your blueprint. But to actually make it work, the program needs to store those numbers somewhere, right? For that, it uses variables. Just think of them as labeled boxes where you can stash pieces of information.
But the computer needs to know what kind of information you're putting in those boxes. Is it a number? A letter?
And that's where data types come in. You basically have to tell C, hey, this box is for a whole number. That's an int. This box over here is for a decimal number. That's a float. Or this one's just for a single character, which we call a char. All right, so you've got your data in the boxes. Now you need to actually do stuff with it. That's what operators are for.
They're the action words, the plus sign for adding, the minus sign for subtracting, and so on.
And as your programs get bigger and more complicated, you start packaging up reusable chunks of code into what we call functions. Think of them like little mini factories that you can call on anytime you need a specific job done. It keeps your code super clean and efficient.
Now, this is a really important idea when it comes to functions, how you give them information. With call by value, you're basically giving the function a photocopy of your data. It can scribble all over the copy, but your original document is perfectly safe. With call by reference, you're giving it the actual original document, so any changes the function makes are permanent. Big difference. And last but not least, every program needs a roadmap, right? You need to direct the flow of traffic. That's done with control structures. The default is sequence, just one instruction after another. Then you have selection, which uses if statements to create a fork in the road. And finally, you have iteration or looping, which is kind of like a roundabout. You just keep repeating a block of code until some condition tells you it's time to exit.
Okay, so you might be thinking, with all this stuff in mind, why on earth are we still talking about a language that was cooked up back in the 1970s? What sees lasting legacy in a world full of shiny new languages?
Well, it all comes back to this one big idea. Being that middle-level language wasn't a compromise, it was its superpower. That unique blend of raw hardware control and high-level human-friendly logic is precisely what allowed C to build the foundation of our entire digital world.
And when we say foundation, we are not kidding. It is the invisible backbone of almost everything. The core of modern operating systems, like Windows, Linux, and Unix, built on C. The languages that came after it, like C++ and Python, they are literally standing on its shoulders. And it is still the king of embedded systems, the silent, unseen code running in your car, your microwave, and countless other devices you use every single day.
And that's really the big takeaway here. The fundamental ideas we just talked about, variables, control structures, functions, these aren't just C concepts. They are the universal grammar of programming. If you understand the logic of C, it's like you've learned the DNA that's been passed down to nearly every other modern language that exists today.
So that leaves us with one last kind of fascinating question to chew on. As our programming languages get smarter and smarter and they start handling more of the boring work for us, what's the one human skill that will always be essential? It's not about memorizing commands. It's about crafting the algorithm, the recipe, in the first place. That pure, creative human logic that has to exist before a single line of code is ever even written.